ready for your mind to be blown when we get into conditional statements today. Okay? There's a lot of stuff coming at you. It's kind of fun stuff. It's pretty interesting. So let's get after it here. So conditional statements, a statement that can be written in the if-then. This is something that you were introduced into algebra last year, and now we're going to expand on it this year. So if we take a look, an if-then statement. I need two statements in order to write as an if-then statement. We usually use P and Q, so statement P and statement Q. And if I look, this is how we write it. P with an arrow pointing to Q. And we read that as P implies Q. So the statement P implies Q. And the hypothesis always follows the if, so in this case it's the P. And the conclusion always follows the then. Okay, that's the thing that you learned last year in algebra. So by looking at this conditional statement down below, if a polygon has 6 sides, then it is a hexagon. So if I took a look, the thing after the if is my hypothesis. That's a tough word. Hypothesis. And the thing after the then is the conclusion. Okay, pretty straightforward. Pretty straightforward. So first thing in your assignment, just identify it. So all you do, you can just put H for hypothesis and C for conclusion, and then just go ahead and write it. And if you're giving it on your test or a quiz, simply underline it and put H, and simply underline the conclusion and put C. That's perfectly fine. Otherwise, on your paper tomorrow, you might actually have to write it out, that a polygon has 6 sides. And same thing for the other one. I'm just going to bring my arrow. Won't go through it, but yeah. Hypothesis after the if, conclusion after the then. You're going to do the same thing in this situation, except you're going to write it in an if-then form as well. And it says identify the hypothesis and conclusion first. I find it easier to do the if-then form first. I'm going to do this part first. That makes it easier. Well, a 5-sided polygon is a pentagon. So I could say what? If a polygon has 5 sides, then it is a pentagon? Or could I go the other way? Could I say if a polygon is a pentagon, then it has 5 sides? I think in this case, either way works. It still would make sense. So feel free to go either way with this one. But make sure that it makes sense. So I'm saying if a polygon has 5 sides, I'll put 5, that's fine, then it is a pentagon. And I like writing it in if-then form first, because then I can just underline and say, oh, here's the hypothesis, and here's the conclusion. Okay, I can just underline it, and I don't have to write it out twice. Conditional statements. This is where it gets a little crazy. It says if Ryan finishes his homework, then he will clean his room. Okay, so we already talked about this. P implies Q. Here's my P, my hypothesis. Here's statement Q. Well, let's make a truth table out of this. So I got P, and I got Q, and now I'm going to put my conditional here. My P implies Q. And we're going to decide, when P is true and Q is false, like what happens here. Just like we were doing the other day with our truth tables. But now we just got our new symbol here with implies, right? P implies Q. Well, P could be true. Ryan could finish his homework, and Q could be true that he actually cleans his room. So our conditional statement would therefore then be true. If Ryan finished his homework, then he cleans his room. Well, he could finish his homework, and he might not clean his room. Well, then that would make this conditional statement false, right? Because he finished his homework, but he didn't clean his room. So that statement is false. Well, let's take a look at when the first part is false. So let's say Ryan does not finish his homework. He still could clean his room, right? So you can't really say that it's false, can you? Because he still cleaned his room. And same thing here now. If I say if Ryan does not finish his homework, then he won't clean his room. Well, from that statement, saying that he doesn't finish his homework, we can't really tell anything from it. So by default, we say that these are true. So what do we notice? If the hypothesis is false, we know by default the conditional is true. Because we can't tell anything, we can't say if that whole condition is true or false because the hypothesis is false. So by default, if the hypothesis is false, P implies Q, the conditional has to be true. So by default, the conditional is true in that case. So if you look, the only time it's ever false is when the hypothesis is true and the conclusion is false. Because I can give a counterexample, and we're going to get into that. So let's try a couple here. It says determine the truth value of the conditional. If true, explain your reasoning. If false, give a counterexample. So this first one, if you subtract a whole number from another whole number. Well, let me think about this hypothesis, this first statement. That's true, right? I can subtract a whole number from a whole number. That makes sense. The result is also a whole number. So now I got to decide, is that true or is that false? So if I subtract a whole number, well, what are whole numbers? Remember, whole numbers are not negatives. They start at 0 and they move up. So I'm not including negatives. So if I took 9 minus 6, I get a whole number. Okay, so far I think it's true. Well, what if I flip the 6 and the 9 around? And I said, not 9 minus 6, 6 minus 9. Well, now I get negative 3. Is negative 3 a whole number? No, it is not. So now this statement right here said this thing is false. And I provided a counterexample right here. So this conditional is false because it's true and then it's false, right? If I go back and look at this, when the first statement is true, the if is true, and the then is false, that makes the whole thing false because I provided a counterexample. What about the next one? When a rectangle has an obtuse angle, it is a parallelogram. Well, I hope you got set off something here. Rectangles have what type of angles? Right angles, don't they? So this first part is false, isn't it? So it doesn't matter what the second part says. I know this whole thing by default is true. By default, it's true. Okay, and we talked about that back here. Because we can't really tell anything from it with the hypothesis being false. So by default, it's true. I know it's kind of confusing to wrap your head around, but that's the way it is. Okay, looking at some other things off our conditionals. So our conditional, we said P implies Q. Well, we also have something called a converse. A converse of the conditional. Well, it just flips the statements around. So basically, if the conclusion, then the hypothesis. Okay, we just flip them around, flip the statements around. Then we have the inverse, which goes back to the conditional, except we negate them both. And then lastly, the contrapositive flips the contrapositive around. And what you're going to find out when we do an example here in a second, we have a couple that are logically equivalent, is what we say. Statements with the same truth value. Every single time the conditional, it's an ugly looking arrow, will be the same as the contrapositive. And the converse will be the same as the inverse. Because logically they are equivalent by how we flip them around and do the negations. And we'll see that in this example here. So let's try something. It says write the converse, inverse, and contrapositive of the following statement. Determine the truth value of each statement. If a statement is false, give a counterexample. Statement, my conditional statement. So I can put this, I can move this down. That's my conditional. If a number is divisible by 2, then it is divisible by 4. Well, first of all, could I have a number divisible by 2? Sure. Well, if a number is divisible by 2, then is it divisible by 4? Not necessarily, right? Can I think of a number? Well, how about the number 6? 6 divided by 2, that's good. But what about 6 divided by 4? Not so good, right? I get a decimal. So true and then false, which makes this whole thing false. And I just provided a counterexample right next to it, right? The number 6. Here's my counterexample. So true and then false makes the whole thing false. It's the only time it makes it false, right? The converse, well, we talked about that. They get flipped around. The P and the Q get flipped around. So this was P implies Q, the conditional. Converse is Q implies P now. So now I got to say, if a number is divisible, put that, by 4, right? I got the conclusion first. Then it is divisible by 2. Well, this changes things, I think, a little bit, right? Because if it's divisible by 4, like 4, 8, 12, 16. So, well, first of all, numbers can be divisible by 4, so that's true. But 4, 8, 16, all those are divisible by 2, aren't they? I can divide all those by 2, so this is also true, isn't it? So if a number is divisible by 4, then it's also divisible by 2. So that makes this whole thing true. Okay, so since it's not false, I don't need a counterexample because it's true, right? If the number is divisible by 4, then it's divisible by 2. Well, we just talked about this logically equivalent thing. The converse and inverse should end up being the same truth value. And let's take a look. So now I'm going back, and P is going to imply Q, but I'm going to negate them both. Not P implies not Q. So if a number is not divisible by 2, if a number is not divisible by 2, then it is not divisible by 4. So if a number is not divisible by 2, which means all of our odd numbers, right? So like 1, 3, 5, well, and plus this is true, isn't it? We just said that's, I can have a number divisible by 2. 1, 3, 5, 7. Then it is not divisible by 4. Well, all numbers that are not divisible by 2 are also not divisible by 4, right? None of these numbers are divisible by 4, so this is also true. So that makes this whole thing true, right? Because if a number is not divisible by 2, all of our odds, then it's also not divisible by 4. And it should be the same thing as the converse, the truth value. They're both true, right? Well, now, conditionals and contrapositives are logically equivalent. So I'm thinking that this is also going to be false, since up top was false, right? We said that this was false, so this will probably be false. Let's try it. So now this is what? Not Q implies not P. So I'll write that down. Not Q implies not P. So I got flipped back around from my last one. So if a number is not divisible by 4, then it is not divisible by 2. Okay, well, numbers that are not divisible by 4. 1, 2, 3, 5, 6, 7, 9, 10. Some of these are divisible by 2, aren't they? 2 is, 6 is, 10 is. So just because this part's true doesn't mean that this part is, because I just proved that. Just because a number is not divisible by 4, I just listed them, doesn't mean it's not divisible by 2, because I just proved that there's some that are. So this is false. This statement is false, because I just proved that 2 is, 6 is, and 10 is. So that makes this whole thing false, right? True and then false. Oh boy, a lot of stuff there, isn't it? Crammed in a lot of things. Just always know that the conditional and the contrapositive always have the same truth value. And then the converse and inverse have the same truth value. And remember, going back here, how this works. P implies Q. Converse, you flip them. Q implies P. Inverse, you flip them back and negate them. Not P implies not Q. And contrapositive, flip that last one. Not Q implies not P. So threw a lot at you there. Hopefully going through some of this will be some good practice, and you'll get it down. Deuces.